Welcome today to the second part of the first lecture. As we discussed last week, we now are going to analyze what happened when there is asymmetric information and actually incomplete information. If you remember, last week, I left you with this program that we maximized under one constraint because it's the constraint that we define as participation constraint. So the constraint that ensures that the agent will accept the contract Why? Because whatever I'm offering, which is given by that part, is actually greater than his reservation utility, which in this case has been simplified by 0. Now we introduce the element of asymmetry in information. What does that mean? It means that the agent the principal, cannot verify what the agent is up to. So cannot verify his level of effort. Now, in this case, I not only have to ensure that the agent is willing to accept my contract, but I also need to verify that he is willing to exert the highest level of effort. Why? Because as we said last week, this is the way to ensure that the performance that he is going to obtain is actually the highest one. And we call this the incentive compatibility constraint, if you recall. Now, today we have to consider, therefore, that we don't just need to maximize the utility function of the principal under constraint number 1, but also under constraint number 2. Now, before we proceed and discuss how this is going to be done, there are a few adjustments that need to be made. Before we get to the economic intuition, I would like to provide you with the mathematical reasoning of what we're going to do. Remember that what we are after. We are after T upper bar and T lower bar optimum, which are the one that are going to be included into the reward schedule of the agent, so that he will not only accept the contract, but also exert the high level of effort. So these are the ones that the principal is happy with, and also the agent is happy with. So these are the payment, the reward schedule, that basically puts the conflict of interest that we discussed last week together, okay? Now, we have two unknown from a mathematical point of view, and we have two equations, right? Because what we're going to happen, it will be that we need to maximize the utility function of the principal, which is this one, normally indicated with a V, under these two equations, these two constraints. Now, for this to happen, as you can see, we have an inequality sign here. So in order to use this constraint to solve and to find out an optimal specific value for T upper bar and T lower bar, this constraint must hold as an equality. So then we will have two equations, number 1 and number 2, into unknown. And we know that we need to simply specify 1 for T upper bar and 1 for T lower bar in order to find our values, our reward schedule, our optimal contract. So what we need to do now, and all the steps that we're going to take now, revolve around prove that this sign of inequality, actually holds as a true equality. Okay? Only after I have proven that, I will be able to use them to find out my optimal values. Okay? So just to recap, summarize what we said before, we have one utility function that needs to be maximized under two constraints. And now we see what kind of assumption needs to be made in order to implement the procedure that we're going to see. But the idea is that since we have two constraints that look like two inequalities, in order to use them to solve my problem, I need to prove that they actually hold as an equality. Only when this is done, I will be able to solve 1 for T upper bar and 1 for T lower bar, put them together and find the optimal value. Okay? So from the economic point of view, it's not obvious that the principal problem is a concave problem. And therefore, we need to make some adjustment in order to use the Lagrange method and then the Kuhn-Tucker condition, and see whether they are necessary and sufficient. The reason why this is not obvious that this the problem is concave is because we have the U function appearing on both sides of the incentive compatibility constraint. So in order to make sure that the problem is concave, we have to make some adjustment, as I mentioned to you. So the first one that we do is that we assume a risk neutrality from the agent, and therefore we can turn U dt upper bar as T upper bar and U dt lower bar, U dt lower bar as equal to T lower bar. This is for the constraint. For the utility function, what we do, we simply change T upper bar as a function h of U upper bar and T lower bar as of U h of U lower bar, where this new level are the ex post utility obtained by the agent in both states of nature. Now, since the constraints are now linear, the set of constraints are now linear, we can rewrite them. We can rewrite them as this is the participation constraint, pi 1 U upper bar plus 1 minus pi 1 U lower bar minus psi cost of effort non-negative, and then the incentive compatibility constraint as 1 minus 1 U lower bar minus psi non-smaller than pi naught U upper bar plus 1 minus pi naught U lower bar. Okay? Now, the utility function instead will look like pi 1 s upper bar minus h of U upper bar plus 1 minus pi 1 S lower bar minus H of U lower bar. Okay, so this is our new program. Participation constraint, incentive compatibility constraint, the utility function of the principal P. How do we proceed? As I said to you before, now that we know that the problem is concave, we know also that the contact conditions are necessary and sufficient. So we can construct the Lagrangian function, which puts together, as we know, the utility function and the constraint by using the Lagrange multiplier. Lambda for the incentive compatibility constraint, and mu for the participation constraint. Okay, now what do we do now? As we know, we are looking for the optimal transfer that we have replaced by U upper bar and U lower bar. So we simply derive the Lagrangian function, partially derive the Lagrangian function with respect to U upper bar and then with respect to U lower bar. So that would look like sine of partial derivative with respect to U upper bar. And what we're going to have here, minus pi 1 H prime U upper bar plus lambda pi 1 plus mu, sorry, pi 1 and minus pi naught that we will call delta pi plus mu pi 1 equal to 0. And equivalently, we will get for U lower bar minus 1 minus pi 1 H prime of U lower bar minus lambda delta pi plus mu 1 minus pi 1 equal to 0. So from the expression above, we can rewrite it as mu plus lambda delta pi divided by pi 1 equal to 1 over U prime of T upper bar that we discussed before, U upper bar. And from the one below, we have mu minus lambda delta pi 1 minus pi 1 equal to 1 over U prime of T lower bar. Okay? These are the first order condition. Now we have to do a little bit of work on this first order condition. For example, we multiply by pi 1 the first and by 1 minus pi 1 the second first order condition, and then we add them together, and we get mu equal to pi1 times 1 over u prime of t upper bar plus 1 minus pi1 times 1 over u prime t lower bar. Now, since t upper bar and t lower bar are going to be positive, and the utility, marginal utility of t upper bar and marginal utility of t lower bar is actually going to be positive, pi1 minus 1 minus pi1 is going to be in between 0 and 1. So we can easily say that mu is strictly positive. For the Cantaker condition that I advise you to revise separately, when the multiplier is strictly positive, that implies that the constraint to which it is associated is actually solved with the equality, which is what, if you remember, we were looking for. So, sorry, mu is associated with incentive compatibility constraint. So that means that the incentive compatibility constraint is binding. Okay? Which means solved with an equality. It also means that it is relevant for the maximization of utility. It means that what the constraint does is actually to determine one of the stationary points, that when we will know whether it's a maximum or a minimum. It means that is actually relevant. Think about, just to make a small digression on that, and having a utility function of that sort. Suppose that the utility function reaches the maximum in that point, okay? If I have a constraint that meets the utility function here, for example, we can see that the maximum has been already reached by the function by itself. What does that mean? It means that the constraint is non-binding. And therefore, the maximum can be found immediately just looking at the utility function, just using the utility function. The constraint, whatever they are, they do not matter. When instead the constraint, for example, meets the function here, so before reaching the natural maximum of the function, that means that the constraint is binding, because it's the constraint that determines where the function reached the maximum. This is where, in between here, I have to find the maximum, and it will be exactly on the constraint. And this is why I can use either that or that function. Okay, so whether the constraint is binding or not, basically define which is the function that you are going to use to find out, to calculate properly your reward schedule. Okay, so far we have proved that one of the two constraints, in particular the incentive compatibility constraint, is actually binding. Now we have to see what happened with the other multiplier. Okay, if we place this equation that we can call 3, just because we have first order condition and second order condition, we can label that as 3. If we place now into first order condition and we solve it, try it as an exercise, you should get that lambda is equal to pi1, 1 minus pi1 divided by delta pi times 1 over u prime t upper bar minus u prime t lower bar. This is all positive. This difference is going to be actually positive because it depends on the argument of the function that we have inside. Since we know that the utility of u upper bar is going to be greater than the one of u lower bar, that basically ensures that this quantity is also going to be positive as well. So if this is the case, also the participation constraint, where is it? Also the participation constraint can be considered solved as an equality, is binding. So now the last thing that we need to do is to find the optimal value for t upper bar and t lower bar. How do we do that? As I said, we just simply solve the two equation, two unknown. You're looking for t upper bar, t lower bar, and this is what eventually you're going to get. T upper bar is going to be a function of psi plus 1 minus pi 1 psi delta pi. Remember that we are using an h function, and t lower bar is going to be given by psi minus pi 1 psi divided by delta pi. Now, there are a few things we need to say about this final results. So first of all, as you can see, now the two reward schedules are not the same any longer. So we don't have, if you remember, the t lower bar, t upper bar equality, which we define as the full insurance. Why is that? Because this is the result of the asymmetry in information. If I cannot verify as a principal what the agent is doing, I have to make sure that it will be in his best interest to exert the high level of effort, which I know that for the agent is actually costly. So what can I do to make him happy to exert the high level of effort? I have to pay him more when he does. I have to pay more when he obtains Q upper bar versus Q lower bar. Okay, because remember that we define T upper bar as the T that you're gonna get if you have the highest level of performance. Okay, so when he gets Q upper bar, I have to pay more than when he gets T lower bar. This is the provision of incentive. Okay. The other things that you can see is that both reward schedules are a function of psi. What does that mean? In this case, it's very easy, as you can see, that is an increasing function of psi. The higher is psi, the higher is going to be the level of t. What does that mean? The higher is the cost in terms of utility that the agent exerts when he does high level of effort, the more I have to reward it. Otherwise, the guy will not be happy to exert the high level of effort. Of course, there are elements that the a principal cannot control. we have inside here delta pi, pi 1 minus pi naught, but on average, it must be sure that the reward schedule is an increasing function of effort, okay? The two are not different. Let's solve this one a little bit inside, because written in that way, you can see that definitely this is going to be bigger than that, because both reward sign, but this adds a term and this subtracts actually a term to the payment, okay? But let's writing this one once again. So this can be written as pi 1 minus pi naught minus pi 1 divided by delta pi. What do you notice? As you can see, the transfer, so I can rewrite it here. The transfer that or reward schedule that the agent is going to get when he obtains the low level of performance is actually negative. What does that mean? It means that I can ask as a principal a compensation to the agent if he doesn't meet, if he doesn't succeed, okay? This is another way of providing incentive. Not only I pay you much more when you do a very good job, but I ask you money back if you do not meet the performance requirements that we agreed in the contract. In this case, as you can see, the agent does not have insurance at all. Why? Because if things go really, really wrong, and we know that there's a component of luck that can interfere, all the risk is going to be borne on him. So this is we can say, a very high, powerful incentive contract for the principal that puts all the risk on the agent. What's the risk of offering a contract of such a way, structuring such a way to the agent? That the agent is going to reject that. He will say, this is not for me. This is actually too much. You are going to be safe, because if things go wrong, all the risk of this bad luck, stochastic variable, things that I cannot control, will be borne by the agent. So this is a contract that penalizes the agent a lot. What's the risk of that? The agent might simply refuse it.